Yeah, so we're actually submitting an abstract called SurfScribe, which is an approach where we want to perform slice prescription or slab prescription very accurately right at the scanner. This is especially helpful for like, imagine like line scan. I would also think like maybe there are some laminar fMRI applications or vessel specific fMRI where we kind of want to put the slice perpendicular to the cortex so that we are actually imaging these intracortical veins or like the laminar structure going in. So this was kind of really motivated by the fact that putting a lot of the line scan and I think just high resolution imaging. If we don't do precise slice or slab placement that is kind of aligned with the cortical anatomy, that can suffer from biases in our analysis. But however, it still kind of remains quite difficult to do everything within the same scan session. So typically, at least for line scanning, what's done is you call the person, you scan them, you acquire like an MP range or an MP2 range in the first session, and then you will perform, run free surfer, get the surfaces, try to figure out where you want to put that line. Um, and then go the next day for the second session, can align the two MP ranges and, find the position to um, place the line. So it kind of requires like this tedious, like two scan type of an approach. So our goal here was to just enable this type of automated MRI slice or slab prescription by using deep learning methods that could construct the cortical surface directly at the scanner. So having said that, let me just go to the figures. This is kind of work done by Karthik, who's postdoc at the Martino Center, where, like I said, we are really looking at how to place these slices very precisely so that they are, orthogonal or perpendicular to the intracortical vessels or other, or to place them in a specific ROI with good accuracy. The application that we're here really focused on is ultra high resolution vascular MRI. But having said that, honestly, this is more of a general approach that you want to use ISMRM as a platform to discuss for potential applications. The idea being that, we scan someone at the scanner, we acquire, say, an MP range or an MP2 range, we can send that MRI directly to a laptop. And then at the laptop, we run cortical surface reconstruction, do whatever analysis we want to. In this case, we want to find like flat regions in the surface so that we can put the line or the slice. So we can perform that step of analysis. And then we figure out, okay, this is where we want to put our slice. And we use the surface vertex and the normal value to automatically change the slice prescription or the field of view prescription at the scanner. So this is really all done in a very automated fashion. And it doesn't necessarily require beyond like figuring out, okay, we want to put it here after looking at the surfaces. So you can kind of see an example here, like the initial surface was just here. And after that, once we run this and we've selected the slice in the visual cortex, the profile changes and we kind of have the slice kind of placed right at the visual cortex. And once we have the slice placed at the visual cortex, we could do some very high resolution imaging and start seeing these intracortical vessels really well. And that kind of further really, motivates us that this kind of working because otherwise we wouldn't see these vessels. So that's really the overview of the entire method. And the innovation here is actually um, running this automatic surface recon and analysis at the scanner. Um, so we did acquire a few different volunteers at the scanner, and here I just show some examples of uh, surfaces that were reconstructed, and this is all done within a minute. So it's really very real time and quite accurate in um, uh, its reconstruction. And here in this image, we kind of show the peel surface, um, mid as well as the white matter surface, so that you kind of see the profiles. Uh, within so we kind of get the surface and the surface normals within a minute, and then it takes a little bit of time, like I think 6 or 7 minutes, to get the parcellations. So within like 10 minutes, you can also get like the full uh, range of surface parcellations, which is what you see in the first row. That can also be used for any kind of slab prescription that we want. So we have all of this available, like I would say, within 10 minutes of your scanning and getting an MP range, and that kind of really helps in just planning for all these single slice and slab acquisitions. So the application that we really focused on was like getting some really um, small intracortical veins. This is, you will see like we are imaging at the scale of like 220 micron in plane resolution. But before that, in order to figure out where to put the slice, like I said, we really need a flat region of the cortex. So we calculated the flat region by looking at surface normals and like just correlations with the neighbors. And you can actually just threshold and you start seeing all these clusters of like just flat regions in your cortex, which would be good, good places or to place your slice. We also additionally kind of validated that, look, these regions are truly flat by looking at the curvature values, which is what you see in the right side. These flatness index, the correlation matrices, when there's a very high correlation, that just means that things are more flat, like the surface normals are very similar, and you kind of see the curvature is very low. So this was just like a validation that, okay, the flatness index kind of works, and you can just then also start uh, planning after we've had this analysis done. And on the left hand side, we kind of show one example of a region that is supposed to be flat, and you can appreciate that actually it is quite flat and low curvature in that region, even qualitatively. It's quite visible. So once we had this flat region, we kind of you just put a slice there with 220 micron in plane resolution and 1 millimeter, 1.2 millimeter um, uh, slice thickness. And this is a pretty important experiment because, most mice studies that are being done are done at the intracortical vessel level and not necessarily at the peel vessel level. And so there becomes a lot of like, um, it becomes a little hard to like compare between the results at the human level and what we see in animals. But it would be nice if we can actually get the exact same anatomy and start doing the analysis at that same level so that they can be translated and compared. Anyway, so on the right-hand side, I kind of show the mice cortex. This is work by Xin Yu. We had done the same type of, just a slice. He had put the slice again um, perpendicular to the laminar profile. And all the black dots that you see are like veins, and the white dots that you see are actually arteries. The arteries are smaller. We need to go at much higher resolution. I think in a primate it was shown like 80 microns or something, 80 or 70 microns, to actually start seeing these arteries. So we don't see the arteries, but precisely exactly as we hypothesized when we put the slice in a flat region, we kind of start seeing all the intracortical vessels, which kind of look like how it resembles how it is seen in high resolution animal imaging. So yeah, and this is just 10 minutes of scan, but honestly, even at 5 minutes of scanning, we still have enough SNR to see this profile. And it's kind of pushing towards, can we start doing some fMRI on these vessels now that we see them? But yeah, this is like the kind of the first step. The grid, but also like more simply said, that we are also able to, uh, for applications that are very specific on uh, putting your slab or slice in a given ROI, like for example, prefrontal cortex. I'm not sure if this is we actually could see the boundaries of our parcellations on these surfaces, and we could uh, decide on a place where we could put the slice and slab, which, as you can see, is also like pretty flat. So we kind of did that for one of our acquisitions, and it was successful. And yeah, that's it. We kind of wanted to show these two applications where we are able to place a slab or a slice in a given ROI, or perform like these flat region analysis for high resolution vessels. And that's pretty much it.
Cool. Thank you, Divya.
Yeah.
I like the dorsolateral prefrontal cortex. It's it's not trivial to find this on the scanner on your 3 projections. It would have been awesome if this method existed a couple of years ago for my study as well, where we tried to kind of do this, and we wasted a lot of time kind of doing functional localizers. You just have it based on Atlas. Yeah, that's cool. So to be clear, the surface reconstruction is not happening on Mars, but it's on this laptop that's directly hooked up to Mars, right?
Yes. So that's what the Mars and that laptop are like connected by an SSH tunnel. So yeah, that's how it works for now. But we are currently working on getting like a Docker on Mars where all of this just runs there. And hopefully we can run a preview there on the scanner itself and do all this. But for now, no, it's just on a laptop. And yeah.
Which is a nice advantage, right? Because you have a GUI available and you can basically pick those areas interactively. Whereas on Mars, kind of you wouldn't have GUI, right? You can have standardized automated processes. So on the bottom one, you do mean central sulcus, right?
Yes, it is the central sulcus. No, it's not precentral, it's central. Yeah. Yeah, sorry. I also am not very sure about, so we did place it in the prefrontal cortex. I'm not very sure if it was truly dorsolateral. I think, yeah, I don't think we're going to include this. We're just going to call it like more central sulci. And
I think the DLPFC would make sense because it's one thing that is being kind of used a lot for TMS, for example, where they use this in working memory. And what they do, you know what they do? They put the coil over the motor cortex and then see until it twitches the fingers or the hand, and then they just move at 2.5 centimeters in front and a bit to the right or something. That's kind of the scientific approach of kind of finding DLPFC. So having a more scientific approach like yours, I think would appeal to those people. I would not remove it. It looks fine to me as well. So usually it is just 2 sulci in front of the central sulcus in the axial view, which matches approximately what how it looks like on the right axial slice as well.
Yeah. And actually here we are also going to kind of add, we did GRE scan in this region. So right now it just shows where we place the slice, but Karthik's kind of working on just getting how that scan looks like. It looks pretty good actually. So we're going to put that as well. There is one important point that I didn't mention. It's not in the images, but it's more in the write-up. All of this also, all our like these high resolution scans also use VNAVs, the navigators. So there is like good motion correction built in to at least some of the results that we acquired for the 220 micron and everything. So I think that's also why they look a bit nice and crisp rather than blurry. Yeah. But
As
yeah,
a as a potential application, I think you could also include in a discussion session that this might be helpful for real-time feedback. Kind of having the entire analysis
yes.
suite at your fingertips on the scanner might be useful.
Yeah, I actually do want to discuss that application more with you. Like we of course didn't have time for ISMRM, but it sounds very interesting. If we could do that with, the infra and super granular layer, like you were saying, feedback. But yeah, for sure.
Maybe one last comment. Maybe you don't
Hmm.
give yourself enough credit with respect to the intracortical arteries. I think in rodents they are much smaller. They are bigger, right? In humans they're smaller. So
Yeah.
it's not only a matter of kind of that we don't have the resolution, but also we don't have the calibers in humans. So which would also be a reason. Then it's just it's not that the method is not good enough. It's just that the physiology is not. It's different.
Yeah. Yeah. Yeah, definitely. Like in the primate, I think it took Jianbao some time to get to like 70 micron and where he started seeing these arteries.